Okay, so do you have any questions? Well, at least two of you were not here last Tuesday. So what we did.
Sorry, is there any way to increase the brightness or something? Contrast? I think there's.
Close the curtains.
Can you draw the? I think there's some missing curtains over there. Thank you.
Slightly better.
Yeah.
Okay, so we are still looking at the scattering problem. So let's see. This was the.
We did the optical theorem. We did the optical theorem, and we were doing the Born approximation, which I don't remember.
I mean, let's just go over all the things we did, just to mention. So this was the our wave function, the incident wave and the scattered wave, and where this function f. Well, I have corrected some factors. F was given as the matrix element of the interaction, the Fourier transform of the matrix element of the potential between the full wave and the in the coordinates and the position ket. And once we obtain this f, we know the scattering cross section. So the question was, how do we calculate this f, defined in this way? Now then we looked at, as we mentioned, the optical theorem, which was basically an observation for the forward scattering amplitude. We take this f. Remember, the f is the scattering amplitude from a state k to a final state k prime. In initial momentum k to a h bar k to a final momentum h bar k prime. So what happens if the particle, when it's scattered, it interacts with the potential, but continues in the same direction? And then we said that if we calculate that and take the imaginary part, we said that it gave us the total cross-section up to a coefficient, which you can just look in the book. Now, the optical theorem is not just, so here we are just doing Schrödinger equation. We have a single particle. Well, you can still apply these results to two-particle systems, but of course, in the two-particle system, you have to separate out the motion of the center of mass, and this is the Schrödinger equation for the relative coordinate, if you want. But it is even valid in particle physics, in any kind of field theory. There, the basic idea is you have an initial state. Here in this single particle picture, that initial state just is specified by the momentum k. The imaginary part of the amplitude, in which the state doesn't change after scattering, is always proportional to the total cross-section. And in particles physics, well, there's a slightly different derivation. The basic idea is we have this S matrix, which is the evolution operator from t is equal to minus infinity to plus infinity. And the T matrix is just defined in terms of the S matrix. S is the identity, which describes no scattering, minus I times T, and this S matrix is unitary, which means that S dagger S is 1, and hence it means that for the T matrix, this equation is satisfied. But this equation is basically the basic idea behind the optic theorem. The left-hand side, the T matrix, is the transition to the final scattered final state. So if you look at the matrix element of the left-hand side, this is just the imaginary part of fkk. Let's say analogous to that one. Well, in the right-hand side, you have a T dagger T. You can just insert an identity, but that just means that you have an initial state scattered into some final states. It can be anything. It can even contain more than one particle, if we are doing particle field theory, for example. and you are just summing over all of them, but that sum is nothing but the total cross section. This is the essence of the optical theorem.
Is there an analog for the real part of FKK? No restriction on it whatsoever?
No, nothing, let's say, useful.
Okay.
We can, of course, come out with an identity involving the real part, but you won't be able to identify it with something else. You see, one of the reasons why we take the imaginary part here. Okay, let's just look at this one, this expression over here. You see, the imaginary part is due to this I eta. And you can write that whole thing as 1 over E minus H0, the principal part, minus I eta, plus I times pi times Dirac delta E minus H0. So that gives us the energy conservation. And the other one, there's not even the energy conservation. And then once we discussed the optical theorem, we went back to our discussion of what is this FKK? How do we calculate it? And the first approximation is, if you want to calculate this psi plus, well, that is approximately e to power IKR. This one. Just use that one as your psi plus, and you will get a correction. Or another way of looking at the same thing, in fact, remember, we had seen that the T matrix was given by V plus 1 over E minus H0 V H0 times T. Vt. No. So, this was the T matrix. And so, of course, you can just write it as an expansion. This is plus I eta. This is V plus V 1 over E minus H0, V plus V 1 over E minus H0, V 1 over E minus H0, V plus all the infinitely many terms. And if V is small enough for in some sense, well, the first term will be a good enough approximation. Well, if we, and remember, this is what FKK, sorry. So let me just check one thing. Now, Fk prime k, kk prime, is minus ml cubed over 2 pi h bar squared, k prime v psi plus. This is the full expression of Fkk. And v psi plus is t times k. That's how we, in fact, how the book defines the state psi plus. So Fkk is minus ml cubed over 2 pi h bar squared, k prime t k, and you can just use this expansion of t. The first term is just v. And then we started looking at some physically relevant cases. For example, we looked at the case of a spheric rotational symmetric or spherically symmetric potential. In principle, all the interactions in nature should be rotational. Nature has rotational symmetry, so all the potentials should have this rotational symmetry in some form. Well, if the potential has the rotational symmetry, Then we can just carry out this. This is just minus m over 2 pi h bar squared. This is the first Born approximation. We can evaluate the angular integrals. And at the end, this just turned out to be I m over h bar squared q from minus infinity to infinity dr r e to the power I q r v of r. Now let's just make one observation though. No, okay. Sorry.
Sorry, are you recording?
No, sorry.
Are you recording?
Yes.
Ah.
Well, here, in making this step up to here, I'm assuming that v of minus r is v of r. You see, the way I obtained this, I had obtained this expression. Well, let's go over them. Well, e to the power I q r is just I q r cosine theta. Phi integral just gives me this 2 pi over here. The overall coefficient is still there. Now we can evaluate the cosine theta integral, which gave me e to the power I q r cosine theta divided by I q r, and this is what we obtained after theta and phi integration. Now, if I assume that v of minus r is the same as v of r, this just becomes I m over h bar squared q. Well, let me just keep the first term. Now, in the second term, I will just replace r with minus r. So that will give me plus from minus infinity to 0, dr r e to the power I q r v of minus r. Well, let's see. R times dr doesn't change sign until this r goes to minus r. And the exponent changes sign. And there's a minus sign in between those two integrals. I just flipped the integration limits. So it became from minus infinity to 0. That brought an additional 0. So that this is my final result at this point. Now let's look at the particular case. Well, this is basically a potential well, a spherical potential well. So within this sphere of radius a, the potential is minus V0. Outside, it is 0. So we are looking at this problem. So this is the integral we need to evaluate. Well, now the integral is from minus a to a. But let's evaluate this integral Well, it would have been an easy integral if I didn't have that r inside the integral. Well, I can write that r as,
You have the V0 and the integral minus V0.
thank you.
Minus nasıl oldu? R sıfırdan sonra.
Well, you see, this is my potential. But then I also generalize that integral to r negative values of r, making this definition. You see, I have this integral. Well, you see, v of, when r is negative, the integral is minus r.
I know the minus radial is undefined.
No, it's not a radial. You see, up to here, no, not up to there. Where was I? Okay, up to here, r is the radial coordinate. If you want, let me just change the name to u. In the first integral, I keep it as u. In the second integral, I define r as minus u. Then, to simplify my expressions, I also make one more definition. V is defined for positive values of its argument, not for negative values. I define it to be symmetric. I define the negative values. I define V for negative values of its argument in such a way that it is symmetric. Then I have this integral over here. It's just u, some integration variable. But I will just use the symbol r instead of u, because originally that integration variable came from the radial distance. Now, I could evaluate that integral if that r was not inside the integrand. I can get rid of it by taking the derivative with respect to q. You see, if I take the derivative with respect to q, that brings down an I times r in front of the exponent. So I cancel I, and so I have this equality. Well, these i's also cancel. I have minus m over h bar squared q v0. The q derivative I can take out of the integral. The remaining integral is e to power I q r divided by I q. Q changes from minus a to a. Minus m over h bar squared q v0 derivative with respect to q e to power I q a minus e to power I minus I q a divided by I q d over dq. That is nothing but twice the sine of qa divided by q. Now let me take the derivatives. Well, the derivative of sine is q times cosine q, no, a times cosine qa divided by q minus sine of qa divided by q squared. So let me write it in a slightly different form. So this is f. So what is the imaginary part of f?
Zero.
What happened to the optical theorem? Hmm?
Total cross section is zero somehow, like that's the
Total cross section is 0, but the differential cross section is not 0. So how come? So what are the? Hmm?
So what does the total cross section of zero mean? It means we're observing nothing around the potential. Like our potential is our target in the lab frame. If we fire something at a detector potential, nothing comes out. Is that what?
Now, if cross section is 0, nothing is scattered.
Nothing is scattered.
So what does 0 mean?
All passes through.
Hmm? No, what the, I'm not talking about the
Like
cross
the
section.
state is no longer is a definite Newton state.
Hmm?
Then the state is no longer a definite Newton state. Second.
No, forget about the scattering.
Okay.
What does 0 mean? Especially when you are doing approximations. You see, we are
Second order corrections.
we are doing an approximation here. We calculated f up to first order, which turned out to be which is proportional to v. And so the differential cross section will be f squared, which is v squared. And the total cross section will be v squared. Now, since we are in calculating f, we threw away everything v squared. So imaginary part of f is 0 up to corrections involving v squared. But the cross section is v squared. You see, imaginary part of f, it is 0 plus corrections of the order of v squared. We don't know that it is 0. The only thing we know that is that the imaginary part of f is of the order of v squared. It's not of the order of v. But sigma, you see, the sigma over the omega is f of k prime squared, which is of the order of v squared, because f is of the order of v.
So this means we always need the second order.
If you want to test the optical theorem, you have to calculate f to second order. You see, then what you will see, you will have f, if you calculate the second order, you will get f1 plus some term times v squared, v0 squared. If you calculate the imaginary part of f2, This will be A, now V0 squared, it's real in this case at least, times imaginary part of A, whatever that is. This will be your A. Now, from this you can calculate sigma t. You will have sigma t from the first order, this is of the order of V0 squared, but you will also have plus terms of the order of V0 cubed plus of the order of V0 to the 4. From the square of this one, you will get V0 4. From the product of these two terms, when you take f squared, you will get V0 cubed. But the imaginary part of f2 will be V0 squared. Only the V0 squared terms will match. Because the imaginary part also has corrections that of the order of V0 cubed, V0 fourth, which we didn't calculate. So we don't know whether they match or not at this moment. They should match. Well, the same thing over here. Imaginary part of f, what we had shown here, is 0 plus corrections of the order of v squared. So the total cross-section starts from v squared. So if you would like to test the optical theorem, we first have to calculate f of the order to the power v squared, calculate the imaginary part of that expression, and then we can test the optical theorem.
But it's not just testing the optical theorem, right? To compute the total cross section using f, I still always need to take it to the order v squared. Because I compute f to first order. It gives me an entirely real function like this one. I can't compute a cross section from this, right? I'll get 0.
No. Well, you see, I can calculate the cross section. I know f. I know the differential cross section. Integrate the differential cross section. From this f, you get v squared. You get the total cross section.
Okay.
I can still calculate the total cross section.
Right. Even from the vanishing first order of imaginary part of f.
Sure, no problem.
Because f itself doesn't vanish, just the imaginary part.
Because you see, I can calculate the total cross section by taking the square of f and integrating over all angles. That is one way of calculating the total cross section. Another way of calculating the total cross section is taking the imaginary part of f. They are the same thing. But you have to be careful about to what order you are doing your computation. Always keep in mind that we are making approximations. Some results that might not make sense to you might be due to those approximations that we are making. Here we are, when calculating f, we are throwing away v squared terms. But the total cross-section starts from v squared, so if you would like to compare the imaginary part of f to total cross-section, you have to calculate both sides up to v squared, or both sides up to v to the 0 power.
Okay. Here we got a completely real f.
Okay.
What happens if I find a 0 f disorder?
If f is 0, then you don't have any.
Cross section is 0?
Well, let's see.
Because we learned again to 1 order, right? So we can't conclude the total cross section is 0 just because f is 0, right? This order.
Let me look at this function.
Okay.
Well, this function is not exactly 0. But you see, if QA is somehow large, which can be if you send a energetic particle, for example, if QA might be such that QA is large, then the first term is negligible, then this is just cosine QA. But cosine QA has infinitely many zeros. So in fact, f has infinitely many zeros. So if you calculate the differential cross-section, as a function of QA, but basically that depends on QA. Well, it will have, so what is its value when QA is equal to 0, by the way?
1 minus 1, so is the constants.
It's just the constants. It's just the minus constants.
How do you say that?
Because since QI equals 0, cos QI equals 1. So
You have 1 over QA over there.
Since 0 is 1.
Hmm? Sine QA over QA when QA is equal to 0 is 1.
Is 1. Since
Cosine QA is also 1.
Oh, 0.
0 over 0. So you have to be a bit more careful than that. But let's see. Sine of QA is QA plus QA cubed over 3. I think that should be enough. So sine of QA over QA is 1 minus QA squared over 6 plus blah blah. We have cosine QA is 1 minus QA squared over 2 plus etc. So when QA is equal to 0, this is just some finite number. Then it goes to 0 at some values. Then it increases, goes to 0. Due to this 1 over QA squared, it eventually goes to 0 as QA is increasing. Well, let me open what we have from the book. There is some scattering data in the book. Yes. Proton scattering over calcium. But keep in mind that the vertical axis is logarithmic. So if it changes by 1, that means it's a reduction by a factor 10. So you see that indeed you do get some almost zeros. So this just looks like the scattering cross-section is some smooth function plus some smooth decaying function plus some other function that goes to 0. It's essentially this. Oh, sorry, let me. So all of them are this function, some smooth cross-section, plus, well, let's say that's background probably, plus some other contribution which goes to 0 regularly. So that basically tells us that this is the proton, when it's scattered on calcium, it is more or less scattered just like from a potential well. And also keep in mind that is these plots are multiplied by some powers of 10. And what else can you say about the position of these zeros?
It's periodic looping, so it has to do with the trade function. So how far about are they?
Now let's see.
820?
No, are they shifting the zeros?
No, I don't think so. I think this is regular chunks, isn't it? I mean, look at the first and second.
Yeah.
Hmm. Are these straight lines for you? There's a slight shift.
Is there, or is that just, like, how can you, I mean, my first guess would be to say experimental error or something, right? Why is this?
You see, Also note that these are calcium 40, 42, 44, and 48. Different number of neutrons. Well, and also keep in mind that this is a plot as a function of theta, the difference between the Q. So let's see, here we have a plot as a function of Q. And remember, K is K plus Q, K prime plus Q if I'm not wrong. So Q, if you want, this is K, this is K prime, or let me say this is K prime, this is K. Initially it's moving in the direction of K, it is scattered by an angle theta. This is Q, and so Q is twice K sine of theta over 2. So larger values of theta basically means larger values of Q. But the zeros are at given values of Q times A. So if Q is larger, that means A is smaller.
Ben buna şey derdim hocam, grafiğe sıfır dedim. O yok, buna değil, bir önceki buraya. Yani yukarıya biraz çıkar mı? Ha burada çünkü sinüs QA bölü QA sıfıra giderken limiti 1. Kosinüs de 1 eksi 1 sıfır yapıyor. Direkt ben sıfır derdim.
What about 1 over QA squared at the beginning? It's 0 over 0. How do you know that it is 0?
The limit
You see, the square parenthesis, I agree with you, the square parenthesis goes to 0 as QA goes to 0. But you see, why don't you say that sine QA over QA also goes to 0? Because sine 0 is 0. Why don't you say that?
goes to 1.
Why? If I use your argument, sine QA goes to 0 if QA is 0, so sine QA over QA should be 0.
It's a determinant of that.
So it is not 0 because sine QA over QA goes to 1, not 0, because you get 0 over 0 in the limit. But you see, if you look at this parenthesis, the square parenthesis does go to 0 if QA is 1, but we are dividing that parenthesis by QA squared. The same situation, you get 0 over 0. I don't know what that is. So whenever you always have to check whether you have 0 over 0 in the limits. And in this case, at least it turns out that in the limit QA goes to 0, this is non-zero. Anyway, back to this graph. So if theta, this cross-section has zeros at given values of Q times A. Now, Q gets larger as theta becomes larger, at least close to 0, let's say. So as theta becomes larger, Q gets larger. Now, let's see. The zeros are at larger values of theta in each one of these lines. So the zeros are at larger values of Q. So that the zero at a larger value of Q means there's a smaller value of A, which tells us that calcium 40 has a smaller radius than calcium 42, which has a smaller radius than calcium 44 and 48. It's not because it is dense, because the number of nuclei is also different. And in fact, if you just say that, okay, each one of the protons and neutrons has a given volume, if you put more of protons and neutrons, the volume should increase. So this is basically what we are experimentally observing. If you put more neutrons to the calcium nucleus, the size of the nucleus increases.
At higher energy Do we get graphs like this explainable in terms of the quark model? Like the difference between isotopes due to just having more quarks rattling around because you have more, I mean, can we make that, do we get the same sort of thing with isotopes, the higher energies?
You see, if you are looking at the calcium molecule,
Hmm.
it's a too complicated system to look at it in the quark model. You see, here you have
Let's say,
around 40 nuclei.
let's say hydrogen nuclei, for example, isotopes. Let's say hydrogen or helium isotopes, for example. Do we get something?
But if you are looking at the hydrogen isotopes, then you get just. In that case, the potential well picture doesn't work so well. You see, here, let's look at this problem. This freshman physics, first year. You have a spherical shell of electrons, let's say, a negatively charged spherical shell. Do you remember the electrostatic potential for this system? It is this one. Well, outside the shell, it just behaves like a point charge, so you get the 1/r potential.
Inside the shell?
Inside, there is no electric field, so the potential doesn't change. So this is a bunch of electrons, a bunch of point charges. And the point attraction centers. The combined effect is more or less a well.
Okay.
But you cannot say the same thing for a single electron.
Okay.
So that our discussion of the potential scattering from a box. This works for the calcium mainly because calcium has many scattering centers. But then it makes it difficult to treat it as a collection of gluons or quarks. In the other extreme limit, when you look at, as you said, if you look at the hydrogen and the isotopes, well, this box picture will not work so well from this well. I mean, scattering from a well picture will not work so well. I don't expect to be exactly such a simple model.
Well, we just shifted well because of the like up down quark and a proton, for example. If you're talking about deep inelastic scattering, up down would also give you just a modified potential well, right? Like, yeah, when I'm talking about like higher energies. If you,
Well, you see, our discussion up to here assumes that energy is conserved. So you have a single particle and single filing particle.
okay.
Now that requires a completely different description, but then this result will not be applicable there. So this is in fact why here it looks at the elastic scattering, because that is the picture we have. A particle comes in and the same particle scatters off with the same energy. And if you take into account inelastic scattering, where, for example, if you, I don't know, let's say you send electrons to atoms, well, some of the energy of the atom can be absorbed by the atom itself. And it might cause excitations of the electron. So that will be an inelastic scattering of the atom. So all of these will basically have different characteristics.
Do we ever treat baryons as potential wells?
Baryons themselves. Have you heard of the MIT bag model?
No. What's I'm asking? Okay. What is the MIT bag model?
Well, it just assumes that the proton is basically a bag.
Bag model. Okay.
Bag.
Yeah, right.
Inside you have the quarks.
Okay.
They cannot go out. There's a pressure inside, so that's your model of the baryon or the meson.
Okay. And is that useful? Like, in what situation is that useful? That description useful?
It worked frustratingly well to describe the masses.
Okay.
You see, if you want to do that computation, I don't know, in QCD, you do pages and pages of computation in this bag model, well, just a couple of pages, let's say at most,
Okay.
and they more or less agree.
Because Ali Wajah right now in particular, we skipped the derivation of the barrier masses, we just went straight to magnetic moments. So I think
The bag model works nice. Okay, so higher order Born approximations. Well, I will skip that. Basically, the idea is more or less the same. You see, you just take this term in your T, and essentially the picture you have is, you see, here we are looking at, this is the region where we have the V. You send the particle, it comes here, it scatters at some point, and it is scattered off. This is the first Born approximation.
Okay.
Now, the second Born approximation, you send your particle, it's scattered once, it propagates, then it is scattered again into the final state. Here you have a V, here you have a V, here you have 1 over E minus E0. That's E minus H0. And in fact, if you calculate F in second order, you say this I eta will bring an imaginary part to F. If you calculate that imaginary part, you will see that it will be the cross-section that you obtain in the first order Born approximation. So optical theorem is valid. Okay, let's give a 10-minute break now, and we will continue with another approximation in the next break, in the next hour.
Just last thing, when we calculate, so I'm given a problem, some potential. I compute